Okay, we'll keep talking about volume here, and I'm going to begin section 6.3. In section 6.2, we talked about the disc and washer method, and in this section we'll introduce the cylindrical shell method, or just simply the shell method, we sometimes say. Some volume problems are very difficult to handle using the methods that we looked at in section 6.2. For example, what if we wanted to rotate the bounded region that you see here, y equal x minus x cubed, x equals 0, x equal 1, and y equals 0 about the y-axis. Okay, and if we were to calculate the volume of that three-dimensional object using the washer method, that would be very difficult in this case because since I'm rotating this region about the y-axis, I know that I would have an integral set up in terms of y, and I would actually have to use the washer method twice, okay, because remember with the washer method you're working with right curve minus left curve. Well, the right and the left curve are the same curve here, okay, so one of the things that I would have to do is I would have to know the coordinates of the local max. That wouldn't be an overly difficult thing to do, but I'd have to know that spot. Also, I would need to solve this equation for x. That would be brutal. Okay, it's not easy to do that, and so there would be some preliminary work that would be, not really preferred in a problem like this if we were to use the washer method. Like I said, you'd have to use the washer method twice in going with that route. So fortunately, there's a method that is called the cylindrical shell method that is easier to use in situations like this. So I've redrawn this curve again, and just suppose this is some arbitrary curve now on an interval AB, and you're going to rotate that about the y-axis. So if I go x units to the right of the origin, and then y units up, y and f of x mean the same thing, then I create this vertical line here. Now, if I rotate that vertical line about the y-axis, that line will create a circular path, okay, and I'd want to follow the path that it takes and calculate the circumference of the circle there. So if I do that for every single vertical line, okay, of course the integral notation represents area, so you're working with every single vertical line being rotated about the y-axis, then you would have this integral created. Okay, the circumference of any circle is 2 pi times the radius, so that's where the 2 pi x comes from. F of x is the height, and the bounds, of course, are the start and end points here on this enclosed region. Now, 2 pi is a constant that can come out of the integral, and inside the integral I'm going to have x times the function. Well, the function in this case, in this example that I'm using, would be x minus x cubed. This is an integral set up in terms of x, and the conditions on x here are 0 to 1. And when you distribute x and then find the antiderivative, plug in your bounds, you get 4 pi over 15. Okay, now this is a lot easier than what was being described up here. Okay, I mean, if you were to do the calculation using the methods from section 6.2, there would be, a minimum page of work, I would say, to do that, whereas what you see here, we just have a one-liner and we're done. Okay. Now, below this, I've kind of outlined the information about the shell method. I've also indicated that on the sheet that we've been referring to, so we can refer to that if necessary. And just like before, if we're rotating about the x or y axes, then the k value is 0. Okay. So let's maybe take a look at an example. Now, this was an example that we had done earlier in section 6.2. This was one that I had you put a star by. That was, let's see, the last problem that we had looked at in section 6.2. We've already done that, okay, and you can look back in your notes, and we were using the disk method and then the washer method also in that problem. And that's fine, you know. Let's go ahead and redo the problem, but by using the shell method. So I've graphed these 4 curves and then shaded in the enclosed region. We're going to rotate this region about the y-axis. Okay, and the nice thing about the shell method here is that we're only going to need 1 integral instead of 2 integrals. We needed 2 in the, when we set this up in section 6.2. So the volume is going to be 2 pi times an integral, where everything about the integral is in terms of x. Now here's one thing, note, that you'd want to pay attention to. So in the previous section, I had mentioned that whenever you're rotating a region about an axis, the variable of integration is going to be the same. But it's switched on us here. Again, if I were to show you what we had done previously, we had an integral set up in terms of y. Well, that's because I was rotating about the y-axis. Okay, the shell method is where you're if you're rotating a region about the y-axis or something parallel to that, you want to use the variable x. If you're rotating a region about the x-axis or something parallel to that, like we'll see in the next example, you'll want to make sure that you're using the variable y. And I would also add, just like before, one of the first things that you'd want to observe is what the variable of integration is, whether that's going to be x or y. The conditions on x are that x is going from 0 to 1. And inside the integral, I'm going to have x times the function. Okay, since I'm rotating about the y-axis here, k is 0. Well, the function is the parabola, x squared plus 1. Stick a dx at the end. Okay, distribute x, and then find the antiderivative, and then plug in your bounds, and you get 3 pi over 2. Now that is the same answer that we had gotten previously, and I mean the method that we had used before wasn't drastically more difficult, okay, but it's just another option. And in some cases I had mentioned just going back to that other page here, it can be drastically more difficult. Okay, so knowing the shell method is handy here. Okay, here's another example. Let's work with the region enclosed by these curves. We got x equal e to the negative y squared. That'd be this bell-shaped curve on its side that I've drawn. And then x equals 0, y equals 0, and y equal 2. And we're going to rotate this region about the x-axis. Okay, so because I'm rotating about the x-axis and using the shell method, the variable of integration is y. So everything has to be in terms of y here. Of course, another difference too is you want 2 pi in front of the integral, not just pi in front of the integral, as we saw in the last section. But everything about this is going to be in terms of y. Well, the conditions on y are where y is going from 0 to 2. And so I can go ahead and write that down. Now it's going to be y times the function. More specifically, it's going to be the function that we see here, x equal e to the negative y squared. And then put a dy at the end. K is 0 since you're rotating about the x-axis. In the next 2 examples, we'll look at rotating about an axis that's not just the x or y axes. Okay, and so now I'd want to calculate this integral. You'd want to use a u substitution. If we let u be negative y squared, du is negative 2y dy. You're going to have a negative 1/2 coming in front of the new integral there involving u. That negative 1/2 will cancel with the 2 there that's in front, going to leave you with negative pi. And also make sure that you change the bounds. Right now they're in terms of y. We got to make them in terms of u. So if y is 0, u would be 0, the lower bound. If y is 2, u would be negative 4, that'd be the upper bound. Okay, so I'm going from, and then inside the integral you've got e to the u du, the y dy part, we're replacing with the du there. Now the bounds don't make sense, right? -4 is smaller than 0, so I want to switch the bounds, throw a negative in front. That'll offset the negative that's already there in front. And so I'm looking at pi times the integral going from -4 to 0 of e to the u du. That looks good now in terms of the bounds. And the antiderivative would be pi times e to the u, which is being evaluated from -4 to 0. When you plug in the bounds, e to the 0 is 1, and then you'll be subtracting e to the -4. Make sure that pi is in front, and that would be the exact answer. And if you were to check, this number would be a positive number. You'll always get positive numbers for calculations in this section. Okay, here's another example. Let's first draw the region enclosed by y equal the square root of x, y equals 0, and x equal 4. I've drawn that, and we're going to rotate that region about the vertical line x equal 5. Okay, now because I'm rotating this about something that is parallel to the y-axis, I know that my integral setup is going to be in terms of x, just like it was over here. All right, so with that said, I'm going to have v equal 2 pi times an integral. The conditions on x are such that x is going from 0 to 4 for this enclosed region. Now, the k value is 5 for this problem. The vertical line is, let's see here, to the left of the region that we're rotating, and so I want x minus k in front of the function. The vertical line is to the right of the region, so I'm going to want k minus x in front of the function. There. Now the k value is 5, and you know I just showed you a formula, okay, but I would also add, you know, still remember what we've already talked about right curve minus left curve. Like the right curve is 5. The left curve would be some x value going to create a vertical line in the shaded region. Okay, so right minus left, that'd be 5 minus x. Times the function. Okay, the function that is what we're working with here is the square root of x. Okay, and when you distribute root x into these two terms, and then I'm using fractional exponents, so then I can use the reverse power rule on the next line. 2 pi times 10/3 x to the 3/2 minus x to the 5/2 times 2/5. We're evaluating that from 0 to 4. Okay, plug in the bounds now. 4 to the 3/2, well, 4 to the 1/2 is 2. 2 cubed is 8. Times 10 is 80, divided by 3, that'd be 80/3. And then over here, 4 to the 5/2, well, 4 to the 1/2 is 2. 2 to the 5th is 32. Times 2 is 64, divided by 5. And when I plug in 0, both of these numbers be 0. When you simplify what you see here, I was getting 416 pi divided by 15 is the exact volume of this 3D object. Okay, and here's one more. Suppose that we have the curves x equal 1 minus y squared, which would be a parabola facing towards the left, and then x equals 0, vertical line. And we're going to rotate that enclosed region there that I've got shaded about the line y equal -2. Okay, now because I'm rotating this about a line that is parallel to the x-axis, my variable of integration is going to be y. Everything about this integral has to be in terms of y. And so v is equal to 2 pi times the integral. The condition on the y values for the shaded region here is that y is going from -1 to 1. And again, you know, make sure that you get everything in terms of the right variable. I've mentioned that probably the most common mistake that I'll see is a student will be using x where they should have been using y, and so, you know, they got their bounds going from 0 to 1 where it should, you know, that's going to mess everything up. Now, inside the integral, we're going to want, let's see here, because that region is being rotated about a line that is below, we're going to want this guy here, right, where we have y minus k in front of f of y. And, you know, if I think about it in terms of top curve minus bottom curve, the top curve would be a y value, creating a horizontal line in this bounded region. The bottom curve, where you're rotating about, is y equal -2. So y minus -2, that'd be y plus 2, times the function in terms of y, x is equal to f of y, right? F of y is 1 minus y squared. Put a dy at the end, and then I'd want to FOIL this out and get my antiderivative. Plug in the bounds. Okay, when I plug in 1, I'm going to have -1/4 minus 2/3 plus 1/2 plus 2. And then minus, when I plug in -1, I'm going to have -1/4 plus 2/3 minus plus 1/2, and then minus 2. Okay, and -1/4 plus 1/4, those will cancel. Well, I simplified this here, and I was getting 16 pi over 3 as the exact answer, representing this the volume of this object. Okay, be sure that you know the shell method and also the disk and washer method. All right, and as I mentioned before, you know, in some cases you want to consider using the shell method instead of the disk and washer method. Okay, really, the classic example of using the shell method is whenever the right curve and the left curve are the same curve, or the top and the bottom curve are the same curve. Okay, that would be like the situation where we'd want to use the shell method. All right, so consider that, and I'll tell you which method to be using when I ask you to compute the volume. But we're now done with the topic of volume. We'll look at one more section, and that'll be the last one that we do for the course there in section 6.4. In section 6.3, the homework is on page 453. Be sure to look at the odd numbered problems listed there.